Hello and welcome to our project demo in CSE 548 Advanced Network Security. My name is Austin.
My name is Ryan.
And I'm Curtis.
So this project focuses on neural networks for anomaly detection. And we're currently demoing task 1, which has to do with building a feed-forward neural network. So to start off, our project, we implemented this in Python. And you'll see if we come to project here, we set up a virtual environment using Python 3.8. Turns out that some of our dependencies are not compatible with the newest version of Python. So we created a virtual environment, which then we imported all of our necessary Python packages to be able to build our neural network as well as test it and then evaluate results. So with that out of the way, I'll go ahead and turn it over to Ryan to explain more in detail about what's happening.
Right. So feed-forward neural network is a pretty simple supervised neural network. That is, the training data is labeled with the stuff that you're trying to get the neural network to recognize. In this particular data set that we're using, the National Science Labs KDD data set, it exposed a number of attacks, denial of service, probing attacks such as port scans, user to root privilege escalation, and remote to local network-based attacks, as well as a handful of normal traffic to compare against. And so we took our training data set and did some pre-processing on it in order to normalize it to what it needs to be for the network to be properly trained. You can see that on screen. We then trained the neural network on the normalized data, which gave us a fitting history. Later, we took a separate test data set, evaluated that, and determined, how good and accurate the test data was based on our train data. And that's mostly the model in a nutshell. The neural network we specifically used was 3 layers. The input layer containing 6 nodes, the second hidden layer containing 6 nodes, and then our final output layer being a single node. Okay, so the next thing we needed to do is run a handful of tests. We wanted to train the model on a few different subsets of the attack types. So you can see on the first line, we trained it on the DOS and normal data. On the second experiment, we trained it on the probe and normal data, so on and so forth. And that allowed us to see how our model performed under different subsets of the training set versus the test data. And while we've been doing this, we've been running the actual models in the background to generate the test data, and I'll hand it over to Curtis to go over our results.
All right, so the key to our experiment, as was mentioned, is that we trained it on different subsets of the attack types, and then we tested it on the 4 distinct attack types to compare our results and to see how training on one attack type affects testing on a different attack type. So this is the output of the training and the testing. And so basically all that's being spit out here is the attack types that were trained on and then the resulting accuracy on a specific attack type. So we basically filled out a matrix of testing on one attack type and training on another. All right, so as you can see in this table, on the leftmost column, we have the attack type that the model was trained on, and then each column represents its accuracy when tested against a different attack. So basically, we pulled out all of the attacks from the data set of each attack type. And what is interesting here is that training on some of the attack types actually can allow you to test accurately on other attack types. And what that suggests is that there's some similarity between attacks in terms of the data. And so one of the questions we asked was, how does the FNN model handle new attacks? And what we found was pretty obvious. If you train on one attack type and test on a different attack type, the accuracy will go down as expected, but not the same amount for each different type of attack. And so the next task was determining how does changing the attack types impact the model. And so to test that, we increased the number of training attacks in the training subset. And we found that pairing different attacks together improved the accuracy differently. And so that really gets into, and so some big examples here, that training on denial of service attacks increased the accuracy of probe attacks, and training on U2R and R2L attacks basically helped each other out in terms of their testing accuracy. And so to investigate that further, we wanted to know what do these attacks have in common? And so what's happening here is we took every sample in the data set and we performed what's called principal component analysis. And it's just a dimension reduction technique so that we can visualize these high dimensional fields in a two-dimensional space so it can be visualized to humans. And what we've noticed is that there's clusters for each of the attacks, and these similarities are actually reflected in the testing and training results. So as you can see, some of the big results here would be that the U2R and the R2L data points almost completely overlap. There's a little bit of extra clusters branching out, but in general, you find those points very close to each other. And that is reflected in our results, where when we trained on one, we tested well on the other. And then there's a lot of overlap between probe and denial of service attacks, but the accuracy that you gain from training on denial of service, for instance, in regards to probe, is lower than what we found for the U2R R2L relationship. And that makes a lot of sense because the overlap is a lot less significant for the DOS and probe attacks, which is pretty clear in this figure as well, because there's that big cluster of denial service attacks in the bottom right of this figure that doesn't really overlap super well with the probe attacks. And so while in general it seems like probe attacks and denial of service attacks have a lot of overlap in their data forms, that's not always the case versus the U2R and R2L, where it's basically always the case. And in general, though, that's our big takeaway from this. Some of the attacks are much more similar in the data, and we can take advantage of that to train on the available data and actually successfully detect attacks of new types, depending on how similar they are.
In task 2, we look at the difference between FNNs and RNNs. To complete this task, we implement different types of neural networks. First, a simple artificial neural network, also known as an ANN, a recurring neural network, or the RNN, a long-short-term memory neural network, also known as LSTM, and then finally a gated recurrent unit, or GRU. Using these 4 different types of networks, we test on time series and non-time series data provided by KDD data sets to simulate a wide variety of various intrusions in a network attack. Our hypothesis is that the types of neural nets that have the capability of looking back in time will perform better and have a higher accuracy than those simple neural net models. And with that, we now will take a look at the implementation for our 4 different neural nets.
Yeah, so for the experiments for this project, first we built the neural network models. So the simple ANN is just a series of dense layers. And then for each of the RNNs, we did a simple layer that used whichever type of RNN node we were using at the time, and then a single dense layer to generate the output, generate the classification. And the experiments went as follows. First, we tested on a non-time series data set. So this was the KDD data set. And we tested each of the neural networks, including the artificial neural network, and compared the accuracy at the end of our training with all of those, and at the end of our testing. And then after that, we wanted to test whether the performance changed with different time series data sets. So first we tested the DDoS data set from the IDS machine learning data set. So this is a series of benign and DDoS events in time series form. And then similarly, we have a time series form of port scan intrusions in the IDS dataset, and we tested both of those. And we used all 4 networks for each of those. And finally, we were curious if we increased the look back specifically for long short-term memory neural networks, would that increase the accuracy? So we started with a look back of 1, meaning we only remembered the previous sample in the stream of features that are being trained and tested on. And in the experiment, we increased that up to 5. So we did 1, 2, 3, 4, 5, and evaluated the accuracy of the model at the end. And I'll turn it over to Ryan for the results.
Okay, so our results in general discovered that for the NSL KDD dataset, that is the dataset without time series data, the FNN performed better than the RNNs. However, using the time series data from the second dataset, the RNNs performed better than the FNN due to their ability to look back. As we can see here, the higher the look back, the more accurate the RNN was, noting that the FNN model essentially has a look back of 0. It evaluates only the current record and without considering how previous records were classified. And the we can also see the loss here, depending on how much look back we have, steadily decreases for the most part within experimental error. And so so basically, whenever you have time series data, the RNN models tend to work better because of their capability to look back. Right, and as the look back increases, you can see that the slope becomes flat, or more flat. So you can see that there's diminishing returns for higher look back.
All right, so for task 3, we looked at the question of, can we use unsupervised learning for detecting these network attacks? And the reason behind that is that, first of all, sometimes you don't have labeled data, and this is a big challenge because none of the other machine learning approaches would necessarily work because they all rely on categorical labeled data. And another reason you might want to use unsupervised learning is that you don't necessarily know how many classifications you're interested in. And by running an unsupervised training approach, you might discover new classes or develop an understanding of the space of the data. Specifically for this task, we use self-organizing maps, which are a type of neural network. They're a fairly simple artificial neural network, but what makes them unique is that they map high-dimensional data that unsupervised to a low-dimensional space. So there's no training on labels, but there is a output that in our case we did 2 dimensions, and 2 dimensions is great because it's you can visualize that as a human being and you can easily differentiate the spaces of the output. And so the hope of an SOM is to put all this high dimensional data in and generate this map that will allow you to differentiate the different types of samples.
And so for the SOM in task 3, we used the CIC IDS dataset, specifically a time series dataset showing benign traffic and port scan traffic. The dataset was labeled, but we removed the labels before training the SOM so that it would not attempt to learn the label features. It would only attempt to learn the other dimensions of the dataset. There were originally 78 dimensions to the data set. We, as Curtis mentioned, compressed that down to 2 dimensions through our training process. and we ended up choosing a SOM of 44 by 44 nodes. This gave a good balance between the time taken to train the model and its accuracy. In order to generate the SOM properly, we do need to first normalize the data. The reason we do this is to make it cluster into the map more easily. Otherwise, we see potential differences of 30,000 or more by using the raw data, and it tended to confuse the SOM and generate errors during the training process. And I'll hand it over to Austin to discuss the results.
All right, so as you can see, in here we have a figure with red and blue dots. In this case, we're looking at the SOM's prediction of whether a row of data is a benign network packet, or if it's a port scan, if it's not benign. And as you can see, the blue here, this is what it sees as benign, and then the red is the attack. And it does, the SOM is extremely accurate in determining, well, it can classify fairly well here between the two different types. In certain situations, you'll see that we have some overlapping purple dots. Now, this is an interesting more or less outlier where it has labeled both as benign and as a port scan. So it's double labeled. And this is reflective on our next graph, which I will pull up now. What you hear, this is the labeling of the benign versus port scan, and taking the prediction from the SOM and then the actual results measured directly from our CSV, so from the training or from the data set. So in this case, you'll see that we have extremely high accuracy where all the blues are the true positives and true negatives. And then you'll see that we have the orange dots, which are the false positives and the false negatives. And in the case where we had the purple dots from before, they're also visible here, as you can't have only true. If you have both, then that's what will happen. So with that said, the SOM in this grid size does a good job at capturing for accuracy while balancing performance.